Hello everyone, my name is Adrián Castelló from Universitat Politécnica de Valencia, and it's a pleasure for me to present the work titled Improving BLIS Code Generation and Portability via TVM. This is a joint effort between Universitat Politécnica de Valencia and Universidad Complutense de Madrid. Both universities are located in Spain. So this is the outline of my talk. We will start with a brief motivation. Then we present TVM, what is TVM, how to use it for the code generation, and how can we exploit the portability between different hardware using TVM. For concluding, I focus the use of TVM for the BLIS code generation from the point of view of algorithms and microkernels. Just to finalize this talk, I will present several experimental results, so in order to make it clear how we can benefit from TVM. Every time a new architecture or a new hardware model is released, it implies an extra effort for code portability. Moreover, if we have different problem sizes, maybe we want to try different algorithms or microkernel sizes, and it also implies an extra not only effort for coding but also for testing and error and comparisons. But can we do this process easier? Well, there exists TVM. TVM is an open source machine learning compiler framework from Apache that is able to generate codes for multiple backends. You can choose CPUs, GPUs, TPUs, and so on. How it works? Well, it exposes a Python API interface, and with user-guided and low-level optimizations, TVM is able to generate a low-level code and assembly code, and the user may specify the compiler like LLVM or ICC, and which is the target. We can target a NVIDIA GPU using CUDA or ARM, for example. Well, it is not easy to explain it, but make it this abstraction. So imagine you have the user's code that want to implement a matrix multiplication, a gem, and we can see how telling the TVM this only line to make a multiplication from a matrix A by matrix B and generate a matrix C. We have here in the pseudocode that is generated for the TVM engine, we can see here how we have the three loops, X, Y, and K. So, and at the end we have C2, it's equal to C2 plus A1 plus by B1 multiplied by B1. And prior to that, we can see all the allocation from the memory. We can do with TVM several optimization like tiling or loop reorder that allow us to make blocking. So for example, the tile instructions, we are dividing the axis 0 and the axis 1 in blocks of 32 by 32. That is here. Now we have a X loop inner and I loop inner, also the outer, so we can see that 32 by 32 are 1000, and we also can make a split for the K loop, and we can see here that 256 by 4 is 1024. The multiplication remains equal here, but we have a tiling of 32 by 32. We can also apply vectorization. Just we have only to say vectorize this loop, that is the innermost loop, and we can see here how the TVM is adding a ramp word here and a broadcast. So what he is doing is just using vectorial instructions for these operations. We can also make array packing like BLIS does. For example, in this case, we are packing B, the matrix B. We are dividing by 32 blocks, and we can see how we change the instruction for making the gem, and we are now multiplying A by pack B. So here there are several arguments that make it clear that all the multiplication is going to be done. As it affects the code, we can see here how we are doing here the pack of the matrix B, and we are using it for calculating the C. We can also do unroll or a pragma OMP parallel, for example, just by indicating the loop and making the order parallel and unroll. So we have here the code that now we are parallelizing the X outer loop, and we have eliminated the most inner loop by adding an unroll. So we have here the 4 iterations that in the previous slide was indicated in the for loop. How we can exploit the portability with TVM? Well, we can select any compiler using the target option with a compiler and the flags. For example, if we want to create ARM code with the neon intrinsics, we might specify the LLVM compiler telling that it's an ARM CPU. We want to use the version 8.2a, and we want also the vector instructions and the neon intrinsics. We could do it in the same way for Intel, and we can specify the data type, float 32, int 8, and so on. How we can apply this TVM code generation to BLIS? Well, we have here the very well-known picture of the BLIS-based algorithm, and I have been trying to reproduce all the hierarchy of the loops by just applying TVM. We are using the base algorithm with these values for MNK, MC, NC, and KC, MR, and NR for the microkernel. So, and we can see here that we have the exact structure, but let me go step by step so I can explain it better. The first time I am dividing the axis 0 and axis 1 by the MC and NC values, and we have reordered it for getting the same structure. We are now in the 5th loop, that is the JC. We can see here how we have created the PC loop by dividing the axis 1 by NC value. Moreover, we have said, okay, you are going to make a packing of B, and it's going to be located in this loop, in the KO, that is here. We can see how the pack B is here and the pack B is here in the TVM. The same for the IC. I here only put the packing of A. We can see in the left the packing here is in this loop, and again we have it here. Also notice that I have added some parallel pragmas so we can achieve better performance. How we create the most inner part of the structure? Well, we are splitting the several loops into factors of the microkernel. We are here right now. We are just arriving to the microkernel, and the microkernel is just generated by unrolling the most general the most general loop and vectorize the other one. So we have here how we have the arm1 the arm0 r1, that is the vector, or is the vectorial register, and we are saying here that this extra packing is like a vectorized load of data from memory to registers, and we have located here, so we ensure that our memory access has strike 1. Okay, and maybe you are okay, well, but how efficient is this microkernel that is generated with TVM? Well, the code in the left is the one generated with TVM. We can see here the vectorized instructions, the non-intrinsics at the end. And if we compare with the same 8 by 8 elements with a manual microkernel using directly nano-intrinsic, we can see that it's very, very, very close. Okay, so we have the loads here, also here, and this is going to make a loop of the microkernel. This is executed in a kernel platform, an 8-core ARM 8.2 version. So we can ensure that the code generated is quite good. We can, as I explained it before, we can generate the BLIS algorithm. What I mean with BLIS algorithm? Well, we know that the BLIS-based algorithm moves the matrix B to L3 and L1, the matrix A to L2, and the matrix C goes to registers. Well, but we can do it in other ways. I mean, we have variants. We can swap I and B because they are very close. The roles of these algorithms are very close. Well, we use the notation of the number of the matrix and which level it's located. So B3 A2 C0 means B3 is in L3 and the packed is in L1. A2 is in the L2. A is located in L2 memory, and C0 means that C is allocated in registers. So taking these three notations, we can just make different algorithms, and there are some cases where A or B may be in registers, but that implies to generate new microkernels with A or B resident in memory. For example, this is the difference between the base algorithm, that is a B3 A2 C0, with the A3 B2 C0. So we can see here how the first loop in the left, that is the JC, is now located in the third place here, and is swapped with the IC. Moreover, here inside, prior to the microkernel, we have the JR and the IR, while in the A3 B2 C0 we have in the other order. Moreover, we can show that here we are doing the packing of the B, while in the other algorithm we are doing the packing of the A. Okay, that in plain code will, maybe it's not a very big effort, but I'm sure that it's less than just changing this order from that order and telling A you have to make the packing of the A in this loop and the packing in the B of this loop, and just changing it. So what we have is two different algorithms just moving several variables. And what about the microkernels? Well, if you remember, I showed you how to generate the microkernel that was splitting the loop between the number of the sizes of the microkernel, x, y, and we have only to make a for loop outside this, and we just may have all the combination. This, if for a developer, should imply time for making 4x4, 4x8, 8x8, 8x12, 8x4, and so on. And the code, for example, we are here showing the 844 by 4 elements, and we can see here how it's very close to the one that we will achieve by hand. In addition, if we add that we may change the target or the type of the data, and we only have to call the build function with ABC, that are the three elements, and the target that we want, we can have a very huge set of low-level microkernels that may perform close to the original one. Maybe you now are asking, well, and how is the performance achieved by this auto-generated code? Well, we are comparing it in sequential and parallel on an NVIDIA Jetson Xavier, an 8-core Carmel core with Neon intrinsics. We compare with a blast-inspired realization of GEM. For example, with a microkernel of 4x4, this is the values for the experiment and CNC-KC, and we multiply we scale the matrix sizes by a factor. For example, this means that the MNK are the same as MCNC-KC. A scaling factor of 2 means that this is multiplied by 2, by 2, and by 2, and so on. And we can see the U suffix means that we have applied a kind of unroll for the code. And we can see that for the microkernel of 4x4, the TVM generated it's lower. The performance is lower than the manual one. Okay, we are talking about 15 against 17 more or less gigaflops. We are close here with a very huge matrices. When we move to parallel, well, in the 4x4 we lose a bit performance, okay, but it can be done automatically. What happens when we move to 8x8 microkernel? Okay, so we can see that here for some values of the program sizes, the TVM outperform the manual BLIS. And when we move to the parallel approach, the TVM could be the same performance. We can just say that we can achieve a decent performance with this TVM. So in conclusion, we have presented an automatic tool for generating the code of any application, but we are focusing on BLIS because it allows us to generate a lot of microkernels for different architectures. So we can improve the portability just by changing one order, one instruction, and with that change we reduce the development efforts, and at the end the performance attained is very close to the manual code. It has been a pleasure to present this talk, and I expect you to talk with you in the BLIS retreat. See you there. Me jodas que no la he grabado.